Imagine this. You and your friend both buy the exact same model of watch. Perfectly tuned, same battery, same mechanics, same design. If you both start them at the same second, logic says they should always stay in sync. But here's the twist. If you live in a high-rise apartment on the 30th floor and your friend lives on the ground floor, your watch will tick just a little bit faster. Not by hours, not even by seconds, but by billionths of a second per day. Yet those billionths matter. They are the reason GPS satellites need constant correction to work, and they are proof that time itself is not absolute. Time bends, stretches, and runs differently depending on where you are and how you move. This idea sounds insane at first. After all, we grow up thinking time is universal. A second is a second everywhere. But Einstein shattered that assumption over a century ago with his theory of relativity. He showed that time is woven into the fabric of space, creating what we now call space-time. And space-time behaves like a stretchy, flexible sheet, not a rigid grid. Clocks don't measure an invisible background tick-tock of the universe. They measure how space-time itself flows in their particular spot. And that flow can change. Let's break this down with an analogy. Imagine space-time as a giant trampoline. Place a heavy bowling ball in the center. That's Earth. The ball bends the surface of the trampoline, creating a curve. Now place two small marbles at different distances from the bowling ball. The one closer is deeper in the curve. The one farther away is higher up. Both marbles live in the same trampoline, but their experience of height is different. Replace height with time, and you get the basic idea. Gravity bends space-time, and clocks closer to massive objects tick more slowly compared to those farther away. This is called gravitational time dilation, and it has been tested countless times. In one famous experiment, scientists took two atomic clocks, the most precise timekeepers we have, and placed one at the top of a building and one at the bottom. After running them in sync, they compared results. The clock higher up, farther from Earth's center, ticked slightly faster. Just a tiny difference, but measurable. This proves that your watch on a mountain runs a little quicker than the same watch at sea level. But gravity isn't the only factor. Motion also plays a role. This is time dilation due to speed. The faster you move, the slower your clock runs compared to one that's standing still. To visualize this, imagine two identical metronomes clicking in rhythm. If one stays still, its clicks are steady. If the other is attached to a fast-moving train, to an outside observer, its clicks stretch out. Inside the train, nothing feels different. The metronome still clicks normally. But compared to the still one, it lags behind. That's because motion through space and the passage of time are connected. The faster you move through space, the slower you move through time. This creates an incredible consequence. If you could travel near the speed of light, you would age more slowly than people left behind on Earth. This is not science fiction. It's been measured in particle accelerators, where unstable particles live longer when they move at near light speeds. And it's been measured with actual airplanes. Scientists flew atomic clocks around the Earth on jets and compared them to clocks left on the ground. Sure enough, the moving clocks were out of sync when they landed, just as Einstein predicted. So let's connect this to your everyday life. Why does this matter for you and your watch? Because modern technology depends on it. GPS satellites orbit thousands of kilometers above Earth. Up there, gravity is weaker, so their clocks tick faster than ours on the surface. But the satellites are also moving quickly, which slows their clocks down. The combination of these two effects, weaker gravity and high speed, means their time doesn't match ground time. If we didn't account for this, GPS would drift by about 10 kilometers every single day. You'd ask your phone for directions to the nearest coffee shop and end up in the wrong city. The only reason GPS works is because engineers constantly adjust for relativity. The system literally depends on bending time. Here's another way to think about it. Imagine you and your friend are drawing two lines across a piece of paper. You both use rulers that look identical, but it turns out your rulers are stretching and shrinking in subtle ways, depending on where you sit. After drawing, your lines don't match perfectly. That's what happens with clocks in different places. They are measuring sticks for time, but space-time itself isn't uniform. It bends under gravity and shifts under speed. The differences are tiny at human scales, but at cosmic scales they add up. The wild part is that this isn't just about watches or machines. It's about you. Your body is full of molecular clocks, ticking through chemical reactions and cell divisions. In principle, those also slow down or speed up depending on your location and motion. Right now, astronauts on the International Space Station are aging a little slower than you are on Earth. Not by much, just fractions of a second, but it's real. If one of them spent decades in orbit while you stayed here, they would come back slightly younger than their twin. This is the twin paradox, and it's not a paradox at all. It's just how space-time works. Now think about the implications. Time is not some universal stage on which events happen. Time is part of the stage itself, stretching and curving depending on the actors and props. The universe doesn't hand everyone the same seconds. Each person, each clock, each location experiences its own flow of time. Your seconds are not identical to the seconds of someone standing on a mountain, or flying on a jet, or orbiting the planet. We live in a universe where even something as solid as time is relative. This is where the eureka moment kicks in. Suddenly, the strange idea that your watch ticks differently in different places makes sense. It's not about faulty gears or bad batteries, it's about space-time itself. Gravity bends it, motion twists it, and your watch simply follows along. The next time you look at your wrist, you're not just checking the hour. You're holding a tiny device that's keeping pace with the warping fabric of the cosmos. That ordinary second hand sweeping around the dial is actually tracing the shape of space-time. And that, I think, is one of the most beautiful hidden truths of physics. Here's something even stranger to consider. Time dilation isn't just about comparing watches on Earth or satellites in orbit. It scales up to the entire universe. Black holes, for example, are the ultimate time manipulators. Near their event horizons, gravity is so strong that time slows almost to a halt compared to the outside world. If you hovered close to one for an hour, you could return to find that centuries had passed elsewhere. This isn't science fiction. It's a direct consequence of the same physics that makes your watch tick differently on the ground floor and the 30th floor. The principle is the same, only magnified to extreme levels. The everyday effect on Earth is tiny, but it reveals the same truth. Time is elastic, shaped by gravity and motion. Think about how humbling this is. For most of human history, we thought of time as a kind of cosmic river, flowing steadily everywhere. We built sundials, hourglasses, pendulum clocks, and digital watches under that assumption. But Einstein revealed that time is more like a network of streams, each winding its own path depending on where you are and how fast you move. Your wristwatch isn't ticking against a universal backdrop. It's keeping pace with your personal stream of space-time. That's why the watch on your wrist, the one on your friends, and the one on a satellite above your head all tell subtly different stories of the same universe. The amazing part is that we can measure these differences. Atomic clocks are so precise they can detect changes in time flow caused by moving just a few centimeters higher or lower. That means if you placed a clock on your head and another on your shoes, they wouldn't stay perfectly in sync. The one on your head, slightly farther from Earth's center of gravity, would tick just a little faster. Yes, your head is technically older than your feet. It's a microscopic effect, but it's there. You are literally stretched across different speeds of time right now. That thought alone is enough to bend your mind. Now let's return to GPS, because this is the best example of relativity in action that affects your life every day. Each GPS satellite carries multiple atomic clocks that constantly broadcast their signals to Earth. Your phone listens to those signals from several satellites and triangulates your position. But if the satellite's clocks ran without adjustment, their faster ticking, from weaker gravity, and slower ticking, from higher speed, would throw the entire system off. By the end of one day, your phone would place you kilometers away from your real location. Navigation apps, airplane routes, shipping lanes, none of it would work. Engineers solved this by pre-adjusting the satellite clocks and applying relativistic corrections in real time. In other words, GPS works because humanity learned to bend Einstein's equations into a practical tool. Without relativity, your Maps app would be useless. So what does this mean for us on a deeper level? It means time is not universal. It means that now is not the same for everyone, everywhere. Each place in the universe carries its own rhythm, dictated by mass and motion. You and I are living in slightly different versions of time even as we speak. And yet, these differences are what make our technology precise enough to guide planes across oceans and cars through crowded streets. Relativity is not just a lofty theory. It's the invisible scaffolding holding up modern life. There's also a poetic side to this. When you look at your watch, it feels like a simple object, gears ticking, numbers shifting, seconds passing. But in truth, it's a window into the fabric of reality. That second hand doesn't just sweep mechanically. It traces the curves of space-time, faithfully following the rules written into the universe itself. The fact that two identical watches in different places can disagree isn't a flaw. It's a clue. It's proof that we live inside a cosmic stage that flexes and moves, rather than one that stays rigid and fixed. And here's the eureka moment. Time is not separate from space. They are one fabric, one structure, one stage. When gravity pulls or when motion accelerates, it's not only space that bends, but time itself. That's why your watch on Earth and a satellite's clock in orbit tick differently. They are simply tracing their unique paths through the same flexible stage. Once you see this, the idea that time is universal dissolves, and a deeper, more beautiful truth takes its place. So the next time you check your watch, remember this: it is not just telling you the time. It is whispering the story of space-time itself. It is a cosmic instrument, quietly tuned to the stretch and sway of the universe around you. Every second is local, shaped by gravity, shaped by speed, shaped by the invisible curves of reality. That is why watches tick differently in different places. Not because they are broken, but because they are honest. They are telling the truth of the cosmos one tick at a time. If this discovery made you see your watch in a new way, imagine how many other hidden wonders are tucked inside everyday life. That's what we explore here at How It Actually Works. So if this sparked your curiosity, share this video with a friend who might love the mind-bending truth of relativity. And subscribe for more journeys into the hidden mechanics of the universe, where we turn ordinary questions into extraordinary revelations. After all, understanding how things actually work is the real key to unlocking wonder.